Hi, welcome to my tale of modernising code. Some of that code is nearly 20 years old now. Or how you too can change 7,500 lines automatically and safely to make future changes simpler. By the end of this talk, I hope to have given you an idea of some of the things that you can do with clang-tidy. That's clang-tidy as it's released, but also how you can modify and extend clang-tidy to solve your own problems. And maybe get some of those modifications accepted into the released clang-tidy for others to use and build upon. So I've been programming in C++ for over 30 years, but I'm not really someone who can speak standardese or knows about the intricacies of how C++ is parsed. I've been working with embedded Linux for over 25 years, initially for MP3 players, and for the last 18 years for digital signage media players at BrightSign. BrightSign has a main application written in C++ that makes use of lots of C and C++ libraries on top of open embedded Linux on several different processors. Those libraries include libcurl, GStreamer, Qt, Chromium, MPV, and proprietary code from chip vendors. The main application dates from 2007, but it continues to make use of some C and C++ code from older products. We have about a dozen people working on BrightSign OS itself and many more working on cloud stuff and client applications. BrightSign's main C++ application used static instances of logging classes in each source file. The code was a thin wrapper around Printf and dates from the C++ 98 days. This certainly isn't perfect, but it has worked well enough for many years. The use of static in particular isn't very modern, but it is easy to write. And it makes it easy to enable or disable logging in any particular file at compile time by just tweaking the declaration. So here we have a log instance called debug log. Oh, sorry, I've got the wrong one. Let's try that. Right. Here we have an instance of debug log for the log statement, which will come out in debug builds only. So this log statement only comes out in debug builds only, whereas this one is an error log. So it always comes out in all builds. So there are other classes named never log and always log, and you can just tweak the declaration here to switch them. So in order to implement this, we're going to provide a class that will always log and one that will never log. And we still need to use the preprocessor to distinguish between them for the particular implementation of debug log. This means we can enable extra logging in debug builds that is automatically disabled in release builds. Error log can be always log all the time. So the implementation of never log is straightforward. The functional call operator, bracket, just never does anything. So here does nothing at all. And the compiler can even throw away the format string parameter since it can see that the string is unused. The implementation of the function call operator in always log needs to actually do some work, so it's on the next slide. This could probably now be rewritten using if const expert to avoid the preprocessor conditional compilation, but I haven't tried to do so. I'll not go into detail about this because it's not really important for this talk, but here's a skeleton implementation. It uses standard C-style variable argument lists, which rely on knowing the types of each argument in order to extract them. Printf uses the format string to determine the types. In standard C or C++, there is no compile time type checking. With the correct function attributes, it was possible to get GCC and clang to generate warnings though, but more on that topic later. So you can see that depending on the value of the debug macro, the log statement here will either emit no code at all, or it will emit code to invoke the function call operator on always log. Log error will always emit code to invoke the function call operator. So all was mostly fine. Occasionally, we thought it'd be nice if it were easier to log our own types more easily. We considered using a streams interface, but there was little love for the verbosity of streams. That would have helped with the type safety though, but we never got round to it. Up until 2017, all products had been 32-bit. On a 32-bit Linux, a long is 32 bits. and int64 is of type long. So this required using %LD or %LLD with printf and log statements. The code was riddled with the use of %LL to format int64t and uint64t. So here we've got uint64t being printed using %LLD. But on 64-bit Linux, a long is 64 bits. So an int64t is of type long, which means you need to print it with %LD. There's no single way to specify how to format B that is correct for both 32-bit and 64-bit Linux. If you can think of one, hang on a minute. To be honest, getting all the other format specifiers right is a bit of a pain too. Though the compiler-specific attributes for warnings I mentioned earlier mostly helped, except in this case where they do exactly what you don't want. Despite the warning, the right thing would actually happen, since long is also 64 bits and will be passed in the same way as a long on 64-bit Linux. You get similar warnings on 32-bit Linux if you try to do the opposite. But those warnings were very useful in other cases to detect incorrect format specifiers provoking undefined behavior. That would lead to incorrect output or even crashes. So disabling them was not an option. Although I haven't programmed for Windows in many years, int64t is long even on 64-bit Windows. So this problem occurs if you're targeting a mixture of 64-bit Linux and Windows only too. So I lied when I said there was no single way to specify how to format B. The C standard solution is int-types.h, or in C++, C int-types, which provides macros that expand to the correct string. So here we have A is an int32, T, so we print that using PRID32. And B is an int64T, and so we print that with PRID64. So these macros expand and get concatenated together with the format string. So you can see that PRID32 just expands to D. Oh, interestingly, I've got I there rather than D, but they're the same, D and I. And PRI64 expands to LLD on 32-bit Linux, LD on 64-bit Linux, or for some strange historical reason, I64D on Windows. I think these macros are horrible to read and to type, and as I hope you can see here, I think they're best avoided unless you have no choice. But I did find a better solution. The format C++ library had been on my radar for a while, and I realized that it completely solved this problem. Its printf function uses templates and parameter packs at compile time rather than C variable argument lists at runtime. So it can be much less picky about the exact type of the arguments. So here if we say %LD for B, that works. If we've sent LLD for B, that works too. Even if we just say %D, that works fine. The output's always the same. So I could just use %D for all of those variables. Though it does still require distinguishing between strings and integers. And there's no compile time format checking. But that matters less, since mostly you don't need to get the format specifiers right, and it won't provoke undefined behavior. It does throw exceptions at runtime if the format string is completely wrong, though. For example, if you pass it too many or too few arguments. Oh, sorry, too few arguments only. So here's the new implementation of the always log operator overload, which now uses a parameter pack to forward the arguments on. We need to be prepared for printf to throw an exception if the format string is wrong. We decided that we didn't want such exceptions to escape because we don't want turning logging on to change the behavior of the program. Just logging the error would be better in that situation. This has been a great solution for the following 6 years or so. More information about this transition can be found in my article in ACC Overload issue 145, which is freely available to read online. So having switched to using the format library, the code was now full of unnecessary calls to standard string cstra. So here, when really you can just type it's 2 because format Printf knows how to deal with standard strings. And people were just copying this into new code, making it harder to read. And for sufficiently long strings, less efficient too. At least that's what I thought. But when writing this, I thought I'd better go and check. It turns out that removing the C call generates 2 more instructions at the call site, well, at least on ARH64 and x86-64, but means the implementation doesn't need to walk the string to find out how long it is at runtime. So it's probably strings and roundabouts for performance and very dependent on the exact situation, unless the string to be logged is really, really long. So I'm going to lean in on the readability aspect instead. This led me to my first foray into clang-tidy, which already had a check called readability redundant string CSTRA that removed unnecessary calls to standard string CSTRA and standard string data. So hopefully everyone here is aware of clang-tidy, but just in case, clang-tidy is a tool to perform automated checks on your code, many of which can apply automatic fixes. Many of the checks are customizable. clang-tidy is part of the LLVM compiler infrastructure project, along with the Clang C and C++ compiler itself. You don't need to compile your code with Clang, but your code does need to be able to be compiled with Clang. We still use GCC to compile most of our code, including the code we're fixing here. We needed to fix some things that GCC accepted, but Clang did not. And we also need to tweak the warnings we enable. You can run clang-tidy on a single source file easily enough. It enables a set of default checks, which you can disable and then enable the ones you want. It will modify the original source file automatically if you pass the -fix option here. If you don't, it will just tell you about the things it would have fixed. So this check in particular, which is the modernize loop convert check, turns an old style C++98 for loop using iterators into a new style ranged for loop automatically. And of course, it's turned the dereference here into an instance of the loop variable there. Rather than specifying the list of checks on the command line, you can create a .clang-tidy file in the current directory or in any parent directory. This is useful if you enable a lot of checks or set check configuration options, and you can commit it to source control too. Of course, in real projects, you will have a lot of compiler options to specify include paths for libraries and maybe some preprocessor defines. If you're using CMake or Mason or probably various other build tools, they can generate compile commands.json files that contain all the compiler options for each source file. Our file is about 7 megabytes. It contains the directory to do the build in, the file we're compiling, the expected output file, and all the arguments passed to the compiler. This is the same file as is used by the clang-d language server protocol server, which is used by VS Code and other editors for code completion and feedback. There's a tool called Bear or Build Ear that wraps running whatever build system you are using and generates the compile commands.json file automatically as part of that. I ended up modifying our make files to generate a compile commands.json file themselves, since they had all the information required. So clang-tidy will automatically use the file if it can be found. Of course, you could tell clang-tidy to look at files one at a time, but it would be much faster on current hardware, at least, if it can run in parallel. If any of the fixes that clang-tidy would apply are in header files, then there's a risk of racing against other invocations reading those same files. You'd hope that would be a solvable problem in the tool itself, but apparently it isn't. Perhaps that's because clang-tidy comes with a Python script that runs the tool in parallel across all the files and then applies the fixes in a separate pass afterwards. It's a standalone script in the LLVM repository. Debian installs it as part of its clang-tidy package, and that's how we invoke clang-tidy. clang-tidy can only fix code that would be seen by the compiler. If you use the preprocessor or build system features to have conditionally compiled code, then clang-tidy might not see it. You need to run it with all possible build configurations. And even then, of course, it can't fix code inside #0 or in comments. Each clang-tidy check is implemented as a class that derives from clang-tidy check and overrides a set of virtual functions. The override of the register matches method is responsible for adding abstract syntax tree or AST match patterns for the code that might need to be fixed. Then each time the parser comes across code that matches the patterns, the check method is called. This function can look at the syntax tree and choose to suggest a fix or not based on what it finds. Other overridden methods can be provided to hook into the preprocessor or limit C++ versions the check is enabled for. So these clang-tidy checks are part of the LLVM project code. There isn't really a way I know of to build plugins, although you could write your own tool, standalone tool using an LLVM library called libtooling. So as mentioned on the previous slide, the register matches method adds one or more matches. It does this by constructing expressions using the large library of general-purpose abstract syntax tree matches. The matches form a domain-specific language, or DSL, and are built up to generate specific matches for the constructs that are candidates for the check to fix. Parts of the tree, such as identifier names, can be bound to names to refer to later. Let's look at an example by adding matches to the readability redundant string cstr check for my log calls. So this code is inside the implementation of the register matches method. I need to add a matcher that would match calls to the operator bracket of our logging classes. That matcher is built up out of smaller ones. This being C++, we're going to have to read it from the bottom upwards. So here we're saying we're adding a matcher that matches a C++ operator call for bracket. And the argument 0, which is the this pointer, can be any of the always log class or the never log class. And we'll look at those in a minute. And then for each argument, use the matcher for the string cstr call expression, so it matches cstr calls on every parameter. I'm not really sure exactly what this bit does. I think it doesn't. It just says we don't care about what the parameter is. I'm not really an expert in that bit. So, although we could have substituted always log class into the matcher directly, it's clearer to separate it out so we can give it a name. The never log class expr is exactly the same except for the obvious place. The has canonical type here sees through type defs. So the string cstr call expr matcher was already part of the code, and I could just use it. It creates named bindings to certain parts of the AST, so they can be referred to easily when the check is actually run later to remove the cstr or data calls. I didn't need to make any changes there. So arg is the expression that cstr is being called on. Member is the member function call expression, and call is the entire call being considered. So now to the implementation of the check method that is called each time there is a match when passing the source code. This code was already in the check. It didn't need changing for this new use case. The function needs to extract the information required from the AST to determine whether the check can be applied. If so, it emits a diagnostic explaining what the change is, along with the code change to be made so that it can be applied automatically. So first, we're going to extract those elements of the AST that we bound to names in the matcher into match variables. LVM has its own runtime type information system, so we're going to use that to grab them as being of specific expression types. We need to determine whether the call to cstr used the arrow operator. If it did, then we're going to need to dereference the expression that the method was called on. So, for example, if we've got a pointer to a string and we're calling cstr using the arrow operator, then we need to make sure we turn that into a dereference of the pointer to the string. Whereas if it uses the dot operator, we can just turn that into the identifier for the string. So this might require adding parentheses in addition to adding the dereference operator. The code to do this used to be in the check itself, but it's been moved out to a helper so it can be used elsewhere. It actually contained a bug if the arrow operator was overloaded, which I needed to fix and send upstream. If the call just uses a dot, we just use the expression directly. The extra call to here turns a string reference into an actual string, since there's no implicit conversion. So having worked out what the code should look like without the cstrip call, we can omit the required diagnostic. This will describe the fix, as we'll see on the next slide, as well as apply it automatically if -fix was provided on the command line. In this case, we say that we're going to replace the text of the whole call with the text that we just generated. So after all that, here's the result. Running the check on the code at the top yields the output at the bottom. So you can see that it's put little markers underneath the code that's going to be replaced, and then says what it's going to be replaced with. But of course, the check needs tests. clang-tidy is mostly tested with lit tests, which check that the tool emits the expected messages and applies the expected fix-ups when given certain input. clang-tidy is run on the test file and its output is analyzed. The file is not actually compiled either before or afterwards. These tests help make a rapid edit debug test cycle. It's a bit of a pain to decipher the output and work out what you've got wrong with this. So here we've got the statement that needs to be fixed. We expect two messages, one for each of the arguments that are passed. So that's the next two lines. And then finally, this is what we expect the result after the fix is applied to be. In more than one case, I ended up creating a separate file on its own, just contained the one test that was failing, because the output got very confusing when you have multiple of these in the same file. So now I had my own custom version of clang-tidy that I could run against our code. It fixed 1,000 lines over about 200 files. It was only a one-off operation, so it didn't really matter if I needed to build my own custom version of clang-tidy. But why do we even need to say %d, %u, and %s to differentiate between numbers and strings? C printf relied on the types being inferred from the format string, so it could know how to extract the arguments. Format fprintf doesn't need to do that, since it actually knows the types at compile time. The format library already implemented what would go on to be standard format and standard print in C++ 20 and 23. Standard print uses Python-like format strings that mean it's no longer necessary to specify the type at all in the format string. Maybe I could convert all our log statements to use that instead. Fixing thousands of log statements by hand would be hard work. So it occurred to me that a printf to standard print converter would be something that could be useful to many people. So I set out to write such a check, knowing that I could get it reviewed properly to gain confidence before applying it to our specific use case. Clang's existing parsePrintf string class already knew how to parse printf format strings to generate warnings for them. I thought that maybe that code could be used to help with the conversion, and it turns out it could. So how hard can it be? It's just replacing % something with a pair of curly brackets, isn't it? Well, it was rather more work than I expected, and I now know more than I ever thought I would about printf format strings. Here are a couple of things I learned along the way. Printf format strings conflate the types with how to display them. C integer promotion rules mean that a char is actually passed as an int, so people can, and do, print them as integers. Standard print logically defaults to printing them as characters, because they're characters, so it needs to be explicitly told to print them as integers with the D format specifier. The %d here isn't the most correct way to format a character with printf since at least C99. This %d here. Does anyone know what it really could be. Since I'm pre-recording this, I'll just give you a few seconds to think about it and shout it the answer at your screen. Well, it's %HH, which sort of makes sense if you think of a char as being a short, kind of the opposite of %LL being a long, long. People have a habit of printing signed integers as unsigned and vice versa by using the wrong format specifier, and that works with Printf. It might not always have been strictly portable, though. I think it probably is now, though, since C++ 20 mandates that signed integers are 2's complement, but I wouldn't take my word for that. So both I and UI have the same binary representation here. So they when you print them, you get the same if you flip %D and %U around. A simplistic conversion generates different output, since the signedness is now coming from the type rather than the format string. So you can see here the printf output doesn't match the standard print output. So if you want to ensure identical behavior after converting to standard print, then the check needs to insert casts, since then the type will be correct. But often this doesn't matter. So this is only enabled if strict mode is enabled in the clang-tidy configuration. So these are the casts that got added here during the conversion. So having implemented everything I could think of and writing lots of test cases, I sent the test cases to the author of the format library and the standard format proposal for review. They were kind enough to do so and pointed out that I'd failed to spot that the argument order changed when dealing with width and precision. After a bit of messing about, I realized that, to quote Sean Parent, it's a rotate. This turned out to be less than trivial to solve because the previously mentioned casts and C-straw removal also needed to be done at the same time. Unfortunately, because of the other changes that must be done, I don't think it can actually be a standard rotate. But, you know, I should probably have another go at making the code not have any raw loops. So I managed to get the modernize-use-std-print check accepted into clang-tidy last year, and various improvements have landed since. By submitting it upstream, we get the benefit of wider review that the check is correct. I'm not going to show you the implementation, but these are the files to look at if you're interested. So the converter, the format string converter from printf style to standard format style is in this source file. The check itself is in this source file, and all the lit tests are in this source file. So there's over 1,500 lines of tests in that test file. The check provides configuration options to specify the functions to convert calls to, so you can use it with format print as well as standard print. There are some other features I've not talked about here as well, and you can see the documentation for those. Now, to apply the check to my problem, I've used some extra formatting options here to better show the stuff the check has to handle. I can't just replace the format strings and leave the call the same, because then that check will not be idempotent. Any statements in header files might run through the check more than once. If you need to run the check for multiple configurations, even CPP files might be processed more than once. It's not possible to tell whether conversions had already been applied. At a minimum, we'd end up adding loads of curly brackets every time, breaking everything like we have here. The curly brackets in this case have all been doubled up in this case. So the solution was to cheat and replace the operator bracket calls with a uniquely named method call. And add that method call for testing, and then just search and replace afterwards to get rid of it before committing it. So I invented this format spec method. So writing a proper clang-tidy check would be safer than search and replace in general, but since I could control the name of the temporary method call so that it wasn't ambiguous, that wasn't really necessary in this case. There was some internal discussion about landing with the new function first and then doing a rename as a separate change afterwards. This was popular because we thought it would allow landing the changes gradually, and that seemed safer. But it was unpopular since it would cause churn on lines that would ultimately go back to how they were because they contain no parameter substitution. So we decided to land the whole conversion in a single commit. That way we could also teach Git to ignore the change when blaming. And after the rename, we're left with the desired result. So we have log there with no separate method call, as it was. So that ended up with nearly 5,000 lines changed in about 440 files, but not the ones that didn't use % or curly brackets in the format strings because they didn't need to change. So although I got the underpinnings to land as part of the modernize-use-std-print check, the check for our log classes was too specific for our use case. If you want to look at it, you can find it on GitHub here. But before I could land the results of the conversion, I had to investigate a strange crash that it caused during the unit tests. The crash involved an uncaught exception, calling fork, redirecting file descriptors, non-blocking file descriptors, signals, executing Node.js. It was only reproducible under Valgrind, and the offending call wasn't in the unit test code. Luckily, the problem seemed to be completely reproducible, under Valgrind at least, but all these complexities made it rather hard to run under a debugger, and staring at the problem didn't help much either. But I did have lots of computer time at my disposal, so I decided to get it to narrow down the problem for me. I committed each file that the clang-tidy check had changed, since at this point, before the search and replace step described earlier, they were independent. Then I used git bisect to identify the exact one of those files that introduced the failure. There are loads of guides of how to use git bisect out there on the internet, so I'm not going to talk about that part. Ultimately, the logging before running the check ended up calling the code in the top half of this slide. The problem was due to format fprintf dealing with errors writing the output string differently to format print in the bottom half of the slide. Format fprintf would return an error code, which of course no one ever checks. Format print throws an exception, but that's fine because we catch the exception, right? But then of course we call format print again. This time we don't catch the exception. The crash was due to the different behavior of these two pieces of code. I suspect some of you now can guess how that caused the failure. So this commit each file and bisect technique may well be useful for other large-scale changes too. We haven't seen any problems on the embedded devices themselves yet, but of course I'm tempting fate by saying that. So right back at the beginning of this process, when we were still using C fprintf, GCC and clang would check the format string matched the parameters that were passed. That was really important for fprintf, since getting it wrong could cause undefined behavior leading to crashes or incorrect output. The switch to the format library meant that we lost those compile time checks. C++20 means we could get those checks back. So instead of it being a const char pointer, we pass it as a format string, which means the format string gets checked against the arguments. We haven't actually done this yet since we're still on C++17, but it will be one of the first things we do once we've upgraded our compiler. The error messages aren't great, but they are better than a runtime error. So the line that's wrong is this one, because we've said there are 2 arguments and there's only 1 passed. And then the error it's complaining about is basically invalid arg ID, because these are implicitly argument 0, argument 1 in the format string. So our code for logging is quite simple, but there are well-respected alternatives. The speed log is a modern logging library based on the format library. Perhaps we should move away from our custom code to it instead. We could insert it underneath our always log class if necessary. Alternatively, we could write a check to get clang-tidy to replace all the call sites and then remove all the static class instances. And of course, in C++20, we'd still get error messages for the format string not matching the types being passed. We haven't decided to do this yet, but there are changes afoot in our logging, so maybe we will. So with all that fixed, I started looking for other uses of printf. I identified our long-serving helper function, strprintf, that does an sprintf to a standard string. I could convert these calls to standard format or format, but upstream wouldn't be interested in a check for our own private function, even if many people would have an almost identical one in their code. So I discovered that the absale library provides a version of this function. It's called strformat. And clang-tidy contains other absale checks, so I thought that I'd be able to get a converter upstream. And after a little bit of pushback, I did. So clang-tidy now also has a modernize-use-std-print check. By following the same path as before of implementing a check that's generically useful, I could then adapt it for our own use case. So it's the same format string converter. I needed to tweak it a little bit, but not very much, to convert the printf style format strings into standard format strings. The check itself is in this source file, and there, as usual, a load of lit tests in this file. So in this case, the adaptation required for us was just configuring the check to use a different function. There are no code changes. So with another 1,000 more lines changed, we're getting closer to the 7,500 I promised. Brighton OS has its own command line shell for issuing commands accessible via serial or over the network. The shell had a printf wrapper function. We'd invented a format print-like wrapper years ago, but not converted all the existing callers to it. This is similar to what we've already done, but this time it's a member function. So early on in the development of the modernize-use-std-print check, I'd intentionally stopped it working on member functions because it misbehaved. It turned out this wasn't really necessary, as long as I was a bit more careful about where to replace the function name. In theory, if I'd done this earlier, I wouldn't have had to create a custom check for replacing the log operator bracket calls, but my quick attempts to make that work subsequently were unsuccessful. Perhaps it's because it's an operator, not a method call, I don't know. So with another 500 lines like this changed across a handful of files, we've got to the 7,500 that I promised. Although the new clang-tidy checks and our modifications work well enough for us, they aren't perfect. The checks that originally landed and are in clang-tidy up to and including clang19 expanded all the macros in the format string. This is good and exactly what we want when we're replacing the inttypes.h or cinttypes macros, like those. But other uses of macros are more complicated. Perhaps we could fix cases where macros don't contain format specifiers, as long as we left the macro reference alone because its value might differ between builds. Fixing general macros where the format specifier is behind a macro is hard and dangerous. So in this case, if we were we'd have to go and fix it in the macro, which would be very difficult if that macro changed between builds. So the version that's landed ready for clang20 only expands the macros from inttypes.h or cinttypes. So these get replaced in here, which is what you want. However, if you try and use your own macro, then it just complains that it can't do it. So another problem is in templated code. The call to be replaced here does not depend on the template parameters, but clang-tidy still doesn't seem to notice it. I've not investigated why yet and whether it would be possible to fix that. Luckily for us, such occurrences have been rare. So it's 2024. It's compulsory to talk about AI. Although I didn't really use machine learning stuff in my normal work, I did try it a few times for this. I found that ChatGPT was quite helpful to check that I hadn't missed an easier way to do something and to point me at the right function names to look up. It didn't do the work for me, but it did save me some research time. LLVM didn't have an official policy on the use of AI tools at the time, but this use appears to be compatible with the policy that was published subsequently, since I didn't actually use any of the generated code. I asked it things like, how can I tell if the function decl includes a variable argument list? In this context, how can I tell the difference between a C-style variadic function and a template variadic function? Please write a function to go into LLVM that converts a type to its unsigned counterpart. I'd like to say thank you to everyone on the list that reviewed my new checks. The format library really is great and it continues to improve. There are even plans afoot for embedding expressions in the format strings, like Python F strings. That's P3412. Hopefully my experience will inspire you to make use of these clang-tidy checks and perhaps adapting them when you need to. Compiling clang-tidy takes a lot of CPU time, but it's not difficult to do. Building with GCC binutils LD is quite slow though. You recommend using clang. I'm no C++ language or parsing expert, yet I managed to do it. I just stared at the abstract syntax tree dump for the example code trying to work out what to do. And there's the command for generating that. If you write a general purpose check, then you can get it reviewed and improve it before configuring it or customizing it slightly for your use case. I couldn't find a way to say so without making this presentation confusing to follow, but I did actually upstream my first readability redundant string CSTRA check as one for standard format and standard print. The reviewer explained to me how to make my implementation fix multiple arguments in the same call rather than running the check multiple times. That was the for each argument part. You're probably only going to be fixing your code once, so it doesn't matter if your clang-tidy modifications are a bit hacky and don't make it upstream. But sometimes falling back to search and replace can be quicker and easier when that's all that's required. There are really good guides for getting started. You can look at other similar checks to find ways to do things. There's a list of AST matches that you can browse through looking for inspiration. And I often found that once I got the code to compile, it did do something close to what I wanted. Upstream reviewers are very helpful, but they're busy and can be slow. And it sometimes took me quite a while to understand what their comments were telling me to do. I'm not an LLVM committer. I needed to get the reviewers to land my changes for me. So it's been a pleasure to present this to you today. I hope that I've shown you that making use of clang-tidy and even modifying it is easier than you might have thought and given you some ideas. I'll be in Hublot to answer questions, or you can contact me on Mastodon. And the slides are available to download from that URL. Thank you.
Thank you, Mike. That was a great talk.